In this lecture, we are going to learn about directional derivatives and gradient descent. Firstly, we will look at why gradient is perpendicular to the level surface at each point on the surface. Then we'll see why gradient is the direction of maximum ascent or descent while calculating the change in the function. Lastly, we're going to look at the importance of learning rates value in stochastic gradient descent. So let's write firstly look at why gradient is perpendicular to the level surface. We have represented a curve f here, so let's write f as f. Let f be dependent on three variables x1, x2 and x3. So f is a variable of three, f is a function of three variables. So we take a point right here and call it p. P is equal to c1, c2 and c3. What we are going to calculate now is the change in f which changes in x1, x2 and x3. And we are going to use the chain rule of derivatives for that. So the change in f with respect to change in x1, x2 and x3 can be written as partial derivative of x with respect to x1, change in x1, plus partial derivative of f with respect to x2 multiplied by change in x2. Lastly, partial derivative of f with respect to x3 multiplied by the change in x3. This product can also be represented as a vector multiplication or a dot product. So delta f1, delta x1, delta f2, delta x2, delta f, and delta x3 multiplied right here by a column vector which contains delta x1, delta x2 and delta x3. So these deltas represent a slight movement in x1, x2 and x3 from this point P. So this can also be written as gradient of f with respect to x into slight changes here can be represented by a vector v. So we have right here df So what's interesting about this equation is we have a gradient, we have the total change in function, and we have the individual movements of x1, x2 and x3. What so suppose that P is a point on the surface. So we know that f of P of x1, x2 and x3, we substitute this value here, is 0. And if we move on this function on the surface, there will be slight changes, very small changes in the value of the function. So the function df delta x1, delta x2, delta x3 equal to 0 at P. So if we move along the tangent here or here, very small movements, then the value of change in function will be approximately equal to 0. This conclude that the gradient of x, the gradient of the function, sorry, and the change in the individual variables equal to 0 at the point P. So V here represents the tangential, hence dot product of this being 0 means that delta x f p is perpendicular to this, which is true for all points P on F, hence proved. Next, we are going to learn about directional derivatives and why the gradient gives the direction of maximum ascent and descent. So firstly, we'll look what directional derivative is. So I'll just write the heading here, directional derivative. Just change the color here for the content. So directional derivative is the slope of the function f at hand here with respect to an arbitrary vector or direction u. So to find the gradient along this arbitrary vector u, what we are going to do this, we have our u here, and suppose at this point the gradient comes out to be this. So I'll just take on a random direction for the gradient. What we do now is project this onto u, and since u is a unit vector, so what we get here is gradient with respect to u of function f is gradient with respect to the f dot product with u. So that's it. That's the gradient with respect to an arbitrary direction. So what do we actually mean by, to get a more closer look? This is gradient with respect to x1. So we change the value of x1 slightly and we estimate the change in function with respect to that. Same with x2. We change the variable x2 by a small minute change and the change reflected change in the function is seen. Now we take the same for an arbitrary direction u and calculate the change in function in that direction. And now we're going to use the concept of directional derivatives to prove that the direction of maximum ascent or descent is is this, the gradient of the function x with respect to the variables that represented it. So we're going to find minimum of u such that of this. So we find the direction u in which this term gives the minimum or maximum value. So in case of the minimum value, to find the maximum of this, we'll just add on -1 to whatever result we get. So calculating this minimum of u, this can also be represented as the dot product can be represented in the scalar form. So this becomes u and this becomes. So this is the second Euclidean norm of the function and the arbitrary direction, and we plug in the cos theta here. This, since we know that u is a unit vector, this becomes 1, and this is equal to minimum of u cos theta. So this gives the minimum value when cos theta goes to -1. So there's the minimum value is in the opposite direction of the gradient we have actually proved our result. So this diagram represents a function 4x square plus y square minus 2. I have made a 3D plot of it right here, and as we can see, the 2D contour plot gives a better description of this. So as we can see, the quiver vectors, the velocity vectors, all point towards inside of the curve. That is, these are the gradient vector, and they all point towards the center of the curve, the bottommost level of the curve. And at all contour lines, you can see the gradient vector is exactly perpendicular to the surface. And you can see on the surface plot here too, to each of the contour line and each of the surface has the gradient vector perpendicular to it, and which gives the direction of the steepest descent. We just learned that the gradient delta of f is the direction, that is the negative, is the direction of steepest descent. That is, it will cause the maximum change in the value of x. So suppose we have a point here called, suppose we have a point here x, and we want to the move to the minimum of this function. So what we have is we want to move towards x dash, which is the minimum of this function. What we have here is x, and what we can use is this direction, which will ensure that we reach this path not in such a wavy kind of fashion, but in the shortest way possible, which is the direction of the steepest descent or the gradient. We also plug in one hyperparameter called the learning rate. Learning rate determines the step size that we take to reach from here to here. So this can be a learning rate, or this whole step could be one step. That's a high learning rate. So we will now at last determine the effect of learning rate on reaching this minima. So we consider three conditions for that. Let me draw those curves here. So suppose we have three conditions. I'll draw the plots in here. So this one, so the first plot here, it has negative curvature. Has zero curvature, and this last one will have positive curvature. So I'll draw a negative curvature curve. I'll try my best to draw a zero curvature curve. And lastly, we draw a positive curvature curve. So this gradient will now estimate the descent of this function. So suppose the first function estimates this. So the function actually decreases more rapidly than what our gradient estimated. In the case of zero curvature, the function will estimate precisely. The small variations are caused by my lack of drawing skills. So the estimated estimated drop decrease in the value of x to reach the minima will be calculated perfectly if the function has zero curvature. At last, in positive curvature, the gradient will overestimate the value, overestimate the decrease in the function of x, whereas on the other hand, it is increasing, as we can see. So what the learning rate plays a role here is, suppose we choose a very high learning rate. So let me plot a new point here. Suppose we have a point here and we want to move towards here. That's our goal. Let me choose a more visible color. So yeah, so we want to move from here to here. In all cases, we'll choose the direction of the gradient, but what will matter now is the value of this learning rate. So if we take small steps to reach there, it is most probably the case that with slight deviations, we'll be able to reach this point. On the other hand, if we take a very large learning rate, so suppose this is one step and this is one step, so this learning rate overestimates the decrease in the function. So what this function will do, it will rotate about the curvature. So it's very important to choose the right learning rate for your stochastic gradient descent algorithm. And that is all in this video. Thank you.